to section 1.2, kinds of functions. The goals for this section include being able to define what a function is, working with function notation, the f of x notation, and for the functions given in the textbook, being able to sketch a graph or identify a graph, provide the general equation, describe the functional relationship verbally, and discuss the features of the graph. We'll also want to look at restricted domains and Boolean variables with calculators, computer software, and being able to work with them on paper as well. We'll also want to answer questions like this one. Why is a 3-level pyramid of 5-foot cheerleaders not 15 feet high? Coming up with equations to describe that situation. We'll also want to be able to sketch reasonable graphs of related variables based on experience and knowledge. Alright, so let's start with the functions in the textbook. The first function is the polynomial function. You can see the general format where n in this expression is an integer. So verbally we would say f of x is a polynomial function of x. When we look at the graph, we'd see that the graph crosses the x-axis up to n times and has up to n minus 1 vertices, points where the function changes direction. So here, this particular polynomial crosses the graph 4 times, crosses the x-axis 4 times, and has 3 vertices. The domain, all real numbers. Next, we'll look at the quadratic function, a special case of the polynomial function where the largest power or degree is 2. You're very familiar with this from Algebra 2, or you should be. Here we'd say f of x varies quadratically with x, or f of x is a quadratic function of x. And the graph changes direction only once at its one vertex, and the domain again is all real numbers. Moving on to the linear function, we can't get too much more basic than this. F of x equals ax plus b. Again, a special case of the polynomial function where the degree is only 1. You're all familiar with the graph of a line. Here we would say f of x varies linearly with x, or f of x is a linear function of x. And the features changes at a constant rate as x changes. And the domain again, all real numbers. The direct variation function is another special case. It's a special case of the linear, power, or polynomial function. Again, the degree is 1, but the constant term is 0. So in the first quadrant we get graphs that look like this. And we say f of x varies directly with x, or f of x is directly proportional to x. Goes through the origin. That's how we know it's a direct variation function. And the domain is x greater than or equal to 0 for most real-world applications. We can look at the power function, ax to the b, where b no longer has to be an integer. We can look at when b is less than 0 and when b is greater than 0, because each of these generates a different type of graph. Here we go. When b is less than 0, we can see that the graph is decreasing in the first quadrant with asymptotes on the x and y axis. When b is greater than 0, the graph is increasing in the first quadrant and goes through the origin. We would say f of x varies directly with the bth power of x, or f of x is directly proportional to the bth power of x. And as we were discussing, the graph contains the origin if b is positive. For first quadrant behavior, the domain is non-negative real numbers if b is positive, and positive real numbers if b is negative. So non-negative real numbers include 0 when b is positive. Now we can look at the exponential function, ab to the x, where x is in the exponent. That's how we know it's an exponential function. Here we again have two different cases generating two different types of graphs. If the b value is greater than 1, and if the b value is between 0 and 1. If the b value is greater than 1, then we see what's known as exponential growth. If it's less than 1 but greater than 0, we see exponential decay. And we would say f of x varies exponentially with x, or f of x is an exponential function of x in either case. You'll also notice that in either case, the graph goes through the point f of 0 equals a. So that's where it crosses the y-axis. Both graphs also have the x-axis as an asymptote. For b greater than 1, the asymptote is to the left, and if b is between 0 and 1, the asymptote is to the right of the y-axis. All right, the inverse variation function, another special case of the power function, is when our power is negative. And we can see that it's f of x equals a over x, or ax to the negative 1, or ax to the negative integral power. Being able to write these functions in multiple ways, recognizing their multiple representations, can greatly help you as we proceed through this course. Okay, again, we'll have a couple of different graphs depending on whether our integer negative exponent is odd or even. If it's odd, we see behavior in the first and third quadrants. If it's even, we see behavior in the first and second quadrants, with an asymptote along the y-axis and the x-axis for both. So here we would say f of x varies inversely with x, or with the nth power of x, or f of x is inversely proportional to x, or to the nth power of x. And again, both of the axes are asymptotes. The domain is x not equal to 0, because we can't divide by 0. For most real-world applications, the domain is also x is greater than 0. Alright, finally we have the rational algebraic function, where f of x equals p of x over q of x, where p and q are polynomial functions. Here we'll see numerous types of graphs, but these graphs all have the potential to have discontinuities in them. We'll say f of x is a rational function of x when we have these polynomial over a polynomial. Right? Now, these discontinuities will occur whenever we try to divide by 0, and we can have two different types of discontinuities. We can have an asymptote or a missing point. And we may have additional horizontal asymptotes. That asymptote, when we divide by 0, will be a vertical asymptote. Alright, so that's the end of our basic function analysis.